Today we're going to talk about one of the most important theorems of calculus. And to set it up, we are going to answer the question, how do we calculate the value of an integral? And to set this up, we're going to talk about what is called the fundamental theorem of calculus. And actually, the fundamental theorem of calculus comes in two parts. So first here, we're talking about part 1. We'll get to part 2 in just a minute. And to set up the fundamental theorem in calculus, I want to remind us about the mean value theorem that we talked about in our previous video. So this is technically a review of the mean value theorem. We said that the average value of a function is equal to 1 over b minus a times the integral from a to b of some function f of x dx. And what we also found out is if that average exists, there is also some point c such that f of c is equal to that average for a c that's in between those two values of top and bottom, minimum and maximums, the a and the b. We're going to use this to set up the fundamental theorem of calculus, at least part 1. To set this up, let's let f be a continuous function such that capital F of x is equal to the integral from some minimum value up to a variable x of f of t dt. So we've got this continuous f. And we're going to consider capital F prime of x. Now, the definition of a derivative is that we take the function at x plus h, and we subtract the function at x over h, and then take the limit as h goes to 0 of that result. Well, let's play with that a bit. We're still going to take the limit as h goes to 0. Let's pull that h out front, that 1 over h times. And for f of x plus h, that means we replace the variable in f. That's the x at the top of the integral. We're going to replace it with x plus h. So we have the integral from a to b of, the integral from a to x plus h of lowercase f of t dt minus the regular function f of x, which is just the integral from a to x of f of t dt. Now we're going to massage this a bit. I should have it in parentheses, because that 1 over h goes through everything. We're going to massage this a little bit. First thing we're going to do is we're going to change the subtraction to addition. And we have a property that says we can switch the order of the integration to change the sign in front of it. So when we do that, we get the limit as h goes to 0 of 1 over h times the integral of a to x plus h of f of t dt plus now the integral in the opposite order, x to a, of f of t dt. But what's nice about this is you see if we start on the right with a bottom of x, we're going up to a. And the next one starts at a and goes up to x plus h. There's no gap between them. So we know we can write that as a single integral, which gives us the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of d dt. And this is very interesting because we note from the mean value theorem, which we have up above here, if I took 1 over the x plus h minus x of the integral from x to x plus h of f of t dt, the mean value theorem says that that is going to equal f of c for some c that's an element of, or it's in between the bottom and top values, between the x and the x plus h. Notice that the x and the minus x there in purple subtract out to 0. So what we really have is 1 over h times the integral, just like is inside that limit. Which means that the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt is equal to the limit as h goes to 0 of the f of c. Making that substitution from the integral to the f of c. But what's interesting is h is going to 0, which means as h goes to 0, this interval is going to shrink and shrink, and c is going to get closer and closer to the x, because that plus h is disappearing. There's less and less space. C gets squeezed down until c starts to approach x, which means this is really saying the limit as c approaches x of f of c. But we also know that this is a continuous function. What's nice about a continuous function is with a limit, we can just plug that value for x into c. And so what we end up with is simply f of x. Why is this important? Remember, we started with capital F prime. The derivative of the integral we found out is equal to f of x, the inside function. Let me summarize that with another point here. Number 3, and this is actually part 1 of the fundamental theorem of calculus. If capital F of x is equal to the integral from a to x of f of t dt, then the derivative is simply equal to the f of x function inside that integral. This is part 1 of the fundamental theorem of calculus, that the derivative is the opposite of the integral. The derivative gets rid of the integral. What does this look like? Well, let's do some examples of how we can do this. Let's find the derivative of the integral from 3 to x of cosine of 4t dt. What the first part of the fundamental theorem of calculus tells us is this top value, as long as the bottom value is a constant number, this top value, all it needs to do is get plugged in for the t, because the derivative of the integral is just the inside stuff. It's just the cosine of 4t. I'm sorry. It's just the cosine of 4x. Plug that x into the t. And that's all we have to do to take the derivative of the integral. Now we can make it a little more interesting and say take the derivative of the integral maybe from 1 to x squared of the square root of t dt. The derivative of the integral still says, as long as the bottom number is a constant, that we can plug that variable in for t. But remember, we have a chain rule. The chain rule says we have to take the derivative of the inside stuff. We still have to take the derivative of that x squared. Chain rule. When we plug that x squared in, then we have to take the derivative of the x squared. So we get the square root of t, which now becomes x squared, times the derivative of the x squared, which is 2x. Well, the square root of x squared is x, times 2x becomes 2x squared. Let's do one more where we have to use the chain rule as we take the derivative. Let's take the derivative of the integral from 5 to the cosine of x of 1 minus t squared dt. Again, we're taking the derivative of an integral. So we just plug that top value in for the variable. And so what we end up with is 1 minus cosine squared of x. But then we have to multiply, using the chain rule, by the derivative of the inside, the derivative of the cosine, which is just the sine of x. This one actually simplifies quite nicely because 1 minus cosine squared should look familiar to us. Actually, it's negative sine of x. I lied. The derivative of cosine is negative sine. OK, going back to that 1 minus cosine squared then. 1 minus cosine squared should be familiar because that's equal to the sine squared of x. So sine squared times negative sine squared is, times negative sine is negative sine cubed of x for our final result. So that's part 1 of the fundamental theorem of calculus. It states that the derivative of the integral is the inside function. Derivative and integral undo each other. If that's part 1, let's look at part 2, the fundamental theorem of calculus. Part 2. And this actually is probably the most important part. This is the most powerful theorem of all of calculus. So to set this up, let's let g of x equal the integral from a to x of f of t dt. And then by part 1 of the fundamental theorem of calculus, the derivative of g of x, g prime of x, is equal to the inside function f of x. Part 1 says just take that x and plug it in. Gives us the f of x. What we're going to do is we're going to make up another function. Let's let capital F of x be another antiderivative of f. And if you remember in Calc 1, when we talked about antiderivatives, we said that every function has an infinite number of antiderivatives. They all just differ by a constant. We always needed that plus c at the end when we evaluated them. So g of x and f of x, capital F of x, differ by a constant c. In other words, we could say that capital F of x is equal to our g of x plus a constant, because they're both antiderivatives of the f of x function. We're going to consider two cases. We're going to first consider letting x equal a in the g of x function. If x equals a in the g of x function, going back to the original function, plugging a in for the x, we get the integral from a to a of f of t dt. But the integral from a from anything to itself is always equal to 0. Actually, probably better if I wrote in 2 steps here. Then g of a is equal to the integral from a to a of f of t dt. And we know that's equal to 0. Because integrating from anything to itself is always equal to 0. There's no width. Let's consider another case. Let's let x equal b in g of x. Then g of b is equal to the integral from a to b of f of t dt, which we don't have any way to simplify. So g of b is just that stuff. And then here's where the magic happens. We're going to consider capital F of a. I'm sorry, capital F of b. We'll do the b first. Minus capital F of a. Remember, we said that f is g of x plus c. So f of b is going to be g of b plus c. And then we subtract f of a, which is g of a plus c. However, this is where it becomes interesting. G of a we said is equal to 0. And we've got a positive c minus c is equal to 0. So all that's left is g of b. Or what we're really saying is capital F of b minus capital F of a is equal to g of b. Well, g of b is the integral from a to b of f of t dt. This result is the most powerful result in all of calculus. This is part 2 of the fundamental theorem of calculus, which says that the integral from a to b of f of t dt, the way we evaluate that is we find the antiderivative at the top value, b, and subtract the antiderivative of the bottom value, a, and then we can evaluate any integral. We can find any area between 2 points. Part 2 of the fundamental theorem of calculus. It's the most important theorem of all of calculus, because let's look at what we can do now that we know part 2 is true. First, a quick aside. I want to recall antiderivatives. Antiderivatives are the opposite of a derivative. So if you remember, for example, the derivative rule for an exponent, x to the n, what we would do is we'd pull that exponent out front and then reduce the exponent by 1. Similarly, we can take the integral of x to the n dx by doing the opposite operation for the antiderivative. Instead of decreasing the exponent by 1, we increase it by 1. And then instead of multiplying by the exponent, we divide by that new exponent. And of course, we had that plus c. But what's nice about the fundamental theorem of calculus, as we saw in that proof up above in number 1, the c's are going to subtract out. So we don't really need to worry about the c as long as there's numbers plugged into the integral. There's all sorts of other antiderivatives we can review. For example, the antiderivative of cosine is sine. It's basically all those derivative rules that we saw before work backwards. So if we want to take some examples and say find the integral from 1 to 2 of x squared plus 4x minus 5 dx. We can find the area under this curve between 1 and 2 using the second part of the fundamental theorem of calculus. First, with the x squared, we know we can raise that exponent by 1 and divide by the new exponent, so x cubed over 3, plus 4. For the x, we raise the exponent by 1, x squared, divide by 2, minus 5. Right now, there's an x to the 0, so we raise the exponent by 1, and we get x to the first. Now, if we were just doing antiderivatives like we did at the end of Calculus 1, we'd do a plus c and stop there. But what we're going to do now is we're going to actually evaluate it between 1 and 2. So we'll put this vertical bar. It's not squiggly anymore like the integral. Vertical bar from 1 to 2, meaning we're going to plug in these values. The f of b is that top number being plugged in for each of the x's. So plugging 2 in, we get 2 cubed divided by 3 plus 4 times x, which is 2, squared divided by 2, minus 5x, which is 2. Then we will do a subtraction. Be very careful with this subtraction. What that subtraction is really saying is we're going to change the signs all the way through. Plus becomes minus, and minus becomes plus. Most common error is people don't switch the sign. So instead of a positive x cubed, it's now a negative, and we're going to plug the bottom number in. 1 cubed over 3. The plus now becomes a minus 4 times 1 squared divided by 2. And the minus now becomes a plus 5 times 1. And so what you can see, if I can color code this, the top number got plugged into the original function. The bottom number got plugged into the function with the signs changing. That's what the fundamental theorem of calculus says, is the top number minus the bottom number. From here, we can simplify this using our calculators, which is really nice. Just plugging in what we have here into our calculator, I've got 2 cubed divided by 3 plus 4 times, whoops. Make sure you have the exponent here. 2 cubed out of the exponent divided by 3 plus 4 times 2 squared divided by 2 minus 5 times 2 minus 1 cubed divided by 3 minus 4 times 1 squared divided by 2 plus 5 times 1, enter, and I get this ugly decimal 3.33333, which is not exactly accurate. I want you to change this into a fraction for me, and the calculator does it really nicely. If you hit the math button and hit enter, it changes that to a nice fraction of 10/3. And so that tells us that the area here underneath our curve between 1 and 2 is exactly 10/3. And it's kind of nice that we didn't have to use Riemann sums, and we didn't have to use geometry. We just calculated it using the antiderivatives and the fundamental theorem of calculus. Let's try another example. Let's do the integral from 1 to 4 of x squared plus x divided by the square root of x dx. Well, part of the problem with this one is the ugly form. But if we massage this a bit, it becomes very easy to just use that exponent property on. Remember, the 1/2 power is just, the square root is just x to the 1/2. And then we can divide it by each term, subtracting our exponents. So we have the integral from 1 to 4, and 2 minus 1/2 is 3/2, plus x to the 1 minus 1/2 is 1/2 dx. And now we can use our exponent property to find the antiderivative. With x to the 3/2, we raise the exponent by 1, or 2/2, gives us 5/2. And then we divide by the new exponent. But dividing by the fraction 5/2 is like multiplying by the reciprocal 2/5. Plus x to the 1/2, raise the exponent by 1, and we get 3/2. Multiplying by the reciprocal 2/3. And we're going to evaluate that from x going to 1 to 4 to find our area. First, plugging 4 in, we've got 2 times 4 to the 5/2 over 5, plus 2 times 4 to the 3/2 over 3. And then we subtract the bottom value. Subtract 2 times 1 to the 5/2 over 5, plus becomes minus 2 times 1 to the 3/2 over 3, to get our area between 1 and 4. On the calculator, 2 times 4 to the 5/2 power divided by 5, plus 2 times 4 to the 3/2 power divided by 3, minus 2 times 1 to the 5/2 is multiplying by 1, so that doesn't really do much. Divide by 5, minus 2 times 1 again, divided by 3. And we get this nice ugly decimal. But if I hit math and enter, we'll change it into a fraction, 256/15. And that's the area between 1 and 4 underneath our curve. Part 2 of the fundamental theorem of calculus. Take a look at the homework assignment and try some of these problems. Practice a few of these, and then we will discuss them more in class and answer any more questions that you may have. But with the fundamental theorem of calculus, practice is the best way to master how to use it. Good luck.